Hello! Hi, this is Tim Shue from San Jose State University, and I'm here today to talk about derivatives and rates of change. We'll start by talking about the definition of the derivative, f prime of a, and then look at three ways of looking at the derivative and the slope of the tangent line as instantaneous velocity and as the instantaneous rate of change, and then we'll sort of do a little recap at the end. Okay, so just to get everyone on the same page, I hope, at this point you may have seen, and you certainly will see in the next few minutes, a number of ideas that you can make precise via the idea of limits. So this is why we did all that nonsense about limits before. So there's the idea of the slope of the tangent line to a graph at x equals a. There's the idea of the instantaneous velocity of a moving object at time t equals a. And there's the instantaneous rate of change of some random function f of x at x equals a. So the derivative, what is the point of the derivative? You can say, at least for now, we can sort of say that the point of the derivative is that it unifies all of these ideas in a single mathematical concept. And what is that mathematical concept, you ask? Thank you for asking. So the derivative of a function f at x equals a, which is written f prime of a, is defined to be f prime of a is equal to the limit as h approaches 0 of f of f of a plus h minus f of a all over h. So you take all that stuff, you evaluate that for any value of h, and you take the limit as h approaches 0 if that limit exists. So if that limit exists, then f prime of a exists, and there is such a thing, otherwise there isn't. And in the rest of this video, the point is that we're going to look at different ways of interpreting that number, f prime of a. So beginning with a geometric one, recall that the slope of a line is the rise over run, and the secant line on the graph of a function y equals f of x is between x equals a and x equals a plus h is defined to be the line between the points a comma f of a, that is the point on the graph that with x value a, and a plus h comma f of a plus h, that's the point on the graph with x value a plus h. And this line has, well, if you look at its rise, you go from f of a to f of a plus h, so the rise is f of a plus h minus f of a. And for the run, you go from a to a plus h, so the run is a plus h minus a, which is equal to h. And so the slope of the secant line between x equals a and x equals a plus h is f of a plus h minus f of a over h. Well, that looks familiar. Okay, and now just to illustrate all that, here are some examples of secant lines and their slopes. For a particular example, f of x equals x cubed minus x, and a equals 1. So when h is equal to 1/2, then the slope that you get, f of a plus h minus f of a over h, is 3.75, 3 3/4. And so here's a picture of the corresponding secant line. This goes from a equals 1 to a plus h equals 1.5, and there it is. You know, the point of the secant line is you connect the dots. Okay, so that was a secant line for h equals 0.5. Oh yeah, and so again, the points a comma f of a and a plus h comma f of a plus h are in blue. So now taking smaller h, 0.3, we get a slope, a secant slope of 2.99, and so we get this curve here. So again, this is h.3, slope, secant slope 2.99. I'm like, oh look, still sort of connecting the two dots on the graph, but sort of a little closer to being, just touching the graph, but not quite there. For h equals 0.1, we get a secant slope of 2.31, and we get this picture here. And look, if you take off your glasses and make things a little blurry, well, actually, when I take off my glasses, it makes things a lot blurry, but you guys are younger, so maybe when you take off your glasses, it'll make things only a little blurry, so that you can see that you get the secant line, which almost looks like it just bumps the curve, but not quite. Okay, so we see, when we looked at those pictures, that as h approaches 0, two things happen. One is that the secant lines approach a line tangent to the curve at x equals a, and we call that line the tangent line at y equals f of x at x equals a. And the other thing that happens is that the slopes of the secant line, which are each of which has the slope f of a plus h minus f of a over h, as h goes to 0, well, those slopes approach the limit of that stuff as h approaches 0. That seems familiar. Well, yes, by definition, that is the derivative of f at a, f prime of a. So it follows. Well, this is not really proof, but I hope it sort of makes sense at this point, that f prime of a is the slope of the tangent line to the curve y equals f of x at x equals a. Okay, so returning to our particular example, f of x equals x cubed minus x at x equals 1. So remember that the slope of the secant line between x equals 1 and x equals 1 plus h is f of 1 plus h minus f of 1 all over h. And here it is, slightly simplified. So if you use the limit laws to take this limit as h approaches 0, now I just sort of did it by computer, but you should try to do it yourself with a little algebra. It's not so bad as these things go. Anyway, when you do that, we see that the slope of the tangent line to y equals f of x at x equals 1 is, well, it's 2. There we go. So if we graph y equals f of x, the curve in question, and the secant lines that we had from before, which remember had slopes 3.75, 2.99, and 2.31, and the tangent line at x equals 1, which has slope 2, we get, well, this is exactly what we get here. We get this purple curve, this is the graph of x cubed minus x, and here's the secant line for h equals 0.5, h equals 0.3, h equals 0.1. So as you can see, these lines seem to be approaching this line here, which is in fact this tangent line to the graph of y equals f of x at x equals 1. So again, the secant lines approach the red tangent line, and so the slopes of the secant, and at the same time, the slopes of the secant lines approach the slope of the tangent line, which by definition is the derivative. Okay, so that's one way to think of a derivative as the slope of the tangent line at a given point. All right, here's another way of thinking about the derivative. So remember from reality, what a concept, that the rate, the speed at which you're going is equal to your distance traveled over a period of time divided by the amount of time that you took. If you go 120 miles over 2 hours, you're going 60 miles an hour. So average velocity is the same thing, but in a formula. So for example, so to be specific, if f of t is where you are at time t, is the position of some object at time t, then the average velocity of that object is, between time a and time a plus h is, well, again, average velocity is distance over time. So let's try to make that into a formula using our position function f of t. Well, since we're measuring between time a and time a plus h, if you start at time a and end up at time a plus h, your displacement between time a and time a plus h is f of a plus h minus f of a. And so how much time has passed? Well, if you start at time a and go to time a plus h, the amount of time that's passed is a plus h minus a, and simplifying that, we just get h. And so yay, this should look familiar again. Where have I seen that before? The average velocity of this object is f of a plus h minus f of a all over h. So again, if we take your average velocity between time a and time a plus h, which we just saw was equal to f of a plus h minus f of a all over h, and we take the limit of that as h approaches 0, we can use that to define the idea of instantaneous velocity at time a. That is, the velocity at time a is defined to be the limit as h approaches 0 of f of a plus h minus f of a all over h. Where have I seen that before? Yeah, well, oh look, that just happens to be equal to f prime of a, which, yeah, you knew that was coming. The derivative of f of a. So again, that's another interpretation of the derivative of f at a. F prime of a is exactly the same thing as the instantaneous velocity at time a. Sort of more generally, if your function f represents not a displacement necessarily, but just some sort of general function, that is, for any function f of x using the same reasoning, the change in f between x equals a and x equals a plus h is, well, you start off at f of a and you end up at f of a plus h, so the total change is f of a plus h minus f of a, which means that the average rate of change between x equals a and x equals a plus h is that total change, f of a plus h minus f of a, over how long it took to change, or what you had to change in x to get that change in y. So that's f of a plus h minus f of a all over h. And so again, taking an expression for average rate of change that we just found, f of a plus h minus f of a all over h, and taking the limit as h approaches 0, we can define the instantaneous rate of change at x equals a, the instantaneous rate of change at x equals a is defined to be the limit as h approaches 0 of f of a plus h minus f of a over h. What is that? Okay, you know the drill by now. Yes, that is again f prime of a, the derivative of f at a. So to recap, we've seen that the derivative arises naturally in several different ways. So in terms of a mathematical definition, geometrically in terms of slope, for physically in terms of velocity, and sort of in general and as a rate of change. So each of these four idea areas has an average version and an instantaneous version. So again, starting with the definition. In the definition of the derivative, you start off with a sort of a difference quotient here, f of a plus h minus f of a all over h, and then when you take the limit as h approaches 0, you get the definition of f prime of a. So again, f prime of a is defined to be the limit as h approaches 0 of f of a plus h minus f of a all over h. So that's the mathematical definition of the derivative. And to interpret this in terms of slope, the average version of slope is the slope of the secant line between x equals a and x equals a plus h. And when you take the limit as h approaches 0, you get the slope of the tangent line at x equals a. And remember, because the derivative is a number, it's important to remember this. So people always get confused about this. Because the derivative is a number, the corresponding idea in terms of slope is the slope of the secant line between x equals a and x equals h for the average version, and the slope of the tangent line at x equals a. So remember, the derivative is a number, and so it can be interpreted as a slope. For velocity, the average version of velocity is again the average velocity between t equals at time a and time a plus h. And then when you take the limit as h approaches 0, you get the instantaneous velocity at time a. So this actually gives you some definition of what it means to be going 60 miles an hour at 2 o'clock, even though no time passes at 2 o'clock. And then finally, as a generalization of that, in terms of rates of change, an average rate of change between x equals a and x equals a plus h, it again gives you the same fraction, the same difference quotient, f of a plus h minus f of a all over h. And when you take the limit as h approaches 0, you get the instantaneous rate of change at x equals a, which is again equal to f prime of a. So again, f prime of a is the slope of the tangent line at x equals a. It's the instantaneous velocity at time a, or more generally, the instantaneous rate of change at x equals a. Whew, okay, so we got to the end. So that's it for now. See you next time. Ah!